Hello. No, I cannot talk right now. I'm getting into the elevator. I'm going to talk to you later. Bye. How many times did you have the feeling and the situation that you talk on the phone and suddenly the reception disappears? Like in a magical way. It's happened when you go into the elevator. It's happened when you go into the elevator. It's happened when you go inside a tunnel or a shelter or something like this. So this phenomena is actually really related to our next topic, which is Gauss's law. Gauss's law. And this is a really fundamental idea in physics, especially in physics 2. So I also built a mini elevator, okay? And we're going to try it. I'm going to put my phone inside and I'm going to close it. And although you see here there are holes inside, down below, still because of an effect that's called Faraday effect that you can see using Gauss's law, I would not have any reception at all, okay? So can you please call me? Yes. Let's hope it's going to work.
השיחה מועברת לתא הקולי.
Hi, I'm at the moment not available, or perhaps I'm inside a Faraday cage. Please leave a message at the beep.
Okay, so that's the concept we're going to deal today. And what people do, that I know a story about girls that actually took silver aluminum and fold the buzzer of a clothes shop and then cancel the noise of the buzzer and still close. And Army used this idea actually to be in more intelligence mode, more strictly, and many submarine use this effect. But before we're going to talk about example how to use Gauss's law, I want to give you kind of introduction to the subject. So what we actually going to talk about is about flux. And flux in physics is a general concept. You have flux of raindrops, you have flux of people going through a door, but you also have electric flux. So flux we note with the letter phi, capital Phi, and electric field, we just learned it with the electric field. So what we're really about is understanding what is it a flux. Okay? So before talking about fluxes, let's talk about 2D area. Okay, so you have many kind of areas. You can have, let's say, a coin. Yeah, a coin is kind of a 2D area. You can have a really bizarre area. For example, a blanket. I can take a blanket and take it into the air, and all the time it's a really weird area. But you can take more straightforward. Let's do it here. A more straightforward area, which is a paper, let's say. And even let's take a more simple example. You know, a square, that you have squares like your math papers, right? It's divided into squares. Perfect. And I want to tell you how we can describe this paper. So every small piece in this paper is actually a small element. This whole paper have an area, right? 2D area, which have a finite amount of area, but every chunk of the paper we know have some area. I'm taking out, this is a small unit of area from the paper, and how are we going to call it? If this is A, this is dA, exactly. Okay, perfect, dA. And I want to ask you an interesting question. Can area be present as a vector? Sounds weird, right? Look at my face, okay? You see my area of my face. You know that I'm looking toward you, right? But now I'm looking at that direction. Now looking at that direction. How did you know where this area is going to? You use kind of a vector. You look at my nose, right? So let's think about that, that each element has some normal, a nose, okay? And I like to think about it, that this thing is have a face, and this is the nose, and the nose is perpendicular to this. Okay? Yes? Perfect. So right now I teach you how I can take area and present it as a vector. This vector is called the dA vector. Okay? And it has some magnitude, which is the area. It's this thing. This is the magnitude. And the direction is perpendicular outside in 90 degrees, which is this element. Right? So this is the vector dA, right? And this is the normal vector, right? Which have unit of 1. It's just the direction information. Great. So we understand these things about areas. But we're not dealing with just random area. We're dealing with physics too. So let's put this thing into space. So I'm going to put here an axis, right? This is going to be Z, X, and Y. And in the space, I have electric field. At this point, I have this electric field. And at this point, I have this electric field. And even in this particular point, I have some electrical field that poke this area. This is E, right? I have E in all space, right? Perfect. So now I can actually talk to you about the concept flux. Let's move here. So the flux, the electric field that tries to poke and go through this area, is denoted by this, d phi, okay, of the electric field, equal to electric field vector dot product, okay, it's a dot product. That's the reason I did a bullet circle here. The vector dA. What does this bullet thing means? Dot product, what does it do? It's equal to what? Magnitude. Exactly. The magnitude of E is not a vector anymore. It's only the magnitude. The magnitude of dA, right? And the cosine between the angle, the cosine on the angle between them. This angle, right? You got it? So I like to think about the dot product, the D in the dot product, as die vector. I don't want vector anymore. This is a scalar, right? Scalar product, right? Good. And what I want you to see is, what is the total flux through the paper? The total amount of flux? Integral. The whole equal to the sum of its parts. So it's going to be the integral of all the small fluxes, right? Which is equal to the integral of E dot dA. This is fluxes. Good. And what's the integral is running? On what? What is the boundaries actually? Is the area, the size of the area, right? I sum all the small pieces together and check what is the electric field that poke each one of them, that try to go through each windows, okay? Good. So let's give you kind of intuition about this subject. So let's talk also about rain and also about charge, okay, electric field. So you can think about this as clouds, and here I have some electrical charges, right? Just an idea, okay? Actually, that's what's really happening when you have a thunder strike, right? Okay, you have charges there. Good. And right now the electric field is kind of like a rain, right? It's going that way. The electric field going that way. Okay, like a raindrops, exactly the same. And I'm gonna take an area, for example, this area, and gonna put it here, right there. I'm gonna put here my nice area, okay? And let's assume that the electric field is uniform, which means E is constant, okay? The magnitude of E is constant for this example. Perfect. So what is actually the flux at this situation? So every dA have a face, right? Let's do that it's pointing down. Let's do it like this. And all the dAs are pointing downward. They're looking at the floor. This is the dA. But also, every electric field that tries to go through this, area, is also looking down. So what is the angle between them? Huh? 0, exactly. So what is the flux in this situation? The flux E equal to the integral of E, which we said it's a constant, right? And multiply by dA, and the cosines is 0, which means equal to 1, right? E is a constant, I can take it outside of the integral, and in this specific example, right, E is actually multiplied by integral on dA. If I'm going to sum all the small contribution to the area, eventually I'm going to get A. Understood? Yes? Perfect. Let's do a more complicated one. Instead of putting my paper in this direction, now I'm going to tilt it all the way in that direction. You got it? So it's actually parallel to the rain, okay? So another example would be the same concept, but now I'm going to put it in that direction. So dA is actually looking at you. You see it? This is the small dA. This is how we drew a vector that go outside the board. This notation, right? So this is the nose of the vector, right? This is small unit of dA that build up this area, right? So the rain or the electric field is actually going at that direction, right? The flux did not change when we're talking about the equation. The equation is always the same. It's the definition. It's the integral of E, dA, and what is the between them?
90.
Now it's 90 degrees because dA is pointing at that direction, at the electric field at that direction, so 90 degrees or pi over 2 if you prefer, and this is equal to 0. The flux here is equal to 0. If I would ask you if there, a perfect scenario when there's a massive rain but there's no wind, all the rain go only in this direction, and I'm going to put this paper in the rain, it will not get wet. Okay? The flux of rain through this paper is 0. Okay? I take the assumption that it doesn't have any thickness, right? It's a perfect 2D area, right? But this is the concept. On the other hand, if I'm going to put it that direction, everything going to get wet. Okay? This is clear? Okay, I'm going back to that board. Okay, so now that you got more intuition, I want to take this concept a little bit to a more complicated idea. I want to talk not about general 2D areas. I want to talk about 2D close areas. Okay, we're going to see that these are really, really interesting. Okay, so what is actually a closed area? What do I mean by saying closed area? When I say closed area, that's how I think about it. If I'm going to inject water inside and took my syringe outside and close the small hole, the water is stuck inside. It's a closed area. There's no way around it. For example, if I'm going to take glass, right, and put inside and inject some water inside, right, and then take outside the injection and try to shake it, all the water going to be everywhere because this was not closed, right? If there was a lid on top of it and it was closed, the water were stuck. So we're going to see that, for example, a cube is a closed area, right? If we're going to inject water, nothing going to come out. And a sphere also could be a really nice closed area, okay? So that's what, and also a cylinder could be a closed area, right? Good. But if you're going to take outside something of them, it's going to be open, right? Okay. So in a general case, okay, I'm going to clean this thing. In a general case, let's draw like a really complicated geometry shape. Sweet potato, really ugly sweet potato. Let's give it like the sense of like this is a 3D. Like these shapes and the shape before, the 2D areas, I can divide this thing into small unit of area, right? And still they have small dAs, right? That build this whole area. And now we have a really interesting question we need to ask, to answer, okay? dA have a direction, right? So we need to decide what is the direction of dA. Outside, the nose go outside, or the nose go inside. Okay? What do you think it's going to be? Outside. Why? Because if the nose would not be outside, they would not have air and they're going to die. And we don't want our dAs to die. So this is a convention in math. Okay? The dA's direction for a closed area is always outside. Okay? So all these arrows actually facing outside of this area, not inside. Okay? This is a crucial to understanding this concept. dA is always pointing outside. And a funny way to remember it, if we take the analogy of the nose, think they need to breathe. If they're going to be inside, they're going to breathe all the air that's inside and they're going to die. Okay, good. So when you note that you have a closed area, there's a special mathematic notation. Okay, I'm going to this equation. Okay, special mathematic notation. Remember this thing? Right now you need to add some correction to it. You need to put here a circle. This means that the area A that build off all these small dAs is actually a closed area. Okay? It's a closed area, and I want you to notice something that's not going to be confusing in the future. This closed area actually capture a volume. Understood? If it's a closed area, there is a volume inside, right? But we are dealing only with the area, not the volume inside. Okay? Good. So let's do a classic example. Okay? I'm going to, let's go to this board. Okay? So if, for example, I'm going to have a charge. Let's say a charge Q. Okay? And I want to calculate what is the flux, okay, around this Q. We know how the electric field is behave around a charge, point charge. Do you remember? What is the electric field of a point charge? Is capital K, Q, the charge, divided by R. Right? Squared. Perfect. And also, don't forget that we can change this K into another magnitude. I don't know if you saw it in the lecture, which is 4 pi epsilon naught. Okay? We can do that. It's the same thing. Q R squared. Right? And this is true to all space. Right? All space. So what's going to happen in Gauss's law is that you have the freedom to choose which area that you would like. Okay? I'm going to give you hints and ideas how and which one to use to solve the problem. But for now, I'm going to go with you and tell you the answer. So I'm going to choose for that problem a sphere. In what radius? Specific radius which called R. Okay? And this is actually a complicated area. It's built of what? What's it built of? Small unit of area, dA is right. And what is the direction they are pointing? Outwards, exactly. Exactly, really good, okay? And this one, for example, maybe pointing in that direction, but it's always outward. Okay, perfect. So let's try to solve this integral, okay? And you're gonna see that I'm gonna be really, how to say it in English, exaggerating, okay? And I'm gonna here always draw exactly what is the shape that I choose to have. If it's gonna be cube, I'm gonna put here a cube. If it's gonna be cylinder, I'm gonna draw a cylinder. But in math, the convection is just do a circle. That's all. It means it's closed. That's a concept. Okay? So let's calculate that. So phi E, help me with this thing, is equal to, this is a definition, right? Definition, we do here a small triangle. E dot dA. Good. So what is E? E for all the dAs, it's this equation, right? It's the same equation. It's actually the integral on Q divided by 4 pi epsilon naught divided by R. Which R is it? I want to put here R squared. Look at the drawing. See me in the camera? See? So I'm interested in R of the electric field only in the sphere that interact with these dAs, right? That's all I'm interested about. I don't care about the electric field here, the electric field inside. I don't care about it. So here it's going to be R squared. Understood? Good. Perfect. And now I need to write my dA, right? This is dA. And what is the angle between them? The angle between them is 0. Look at the drawing. So if this is the charge is positive, it's sending electric field outside, right? So it's sending it outside, and my dAs, small chunks, are actually also pointing outside. So the angle between them is 0, which is really nice. Make this constant. Note that this does not care about which dA I am at, right? It's true and holding for all the dAs. So this concept is actually, this thing here is a constant for the integral, right? Because for every dA, R is the same. Okay? If the shape was a little bit weird, it was not true. Okay? Taking this outside of the integral, Q 4 pi epsilon 0 R squared, and I got this integral. What is integral equal to? The size of the sphere, right? The area of the sphere. And I want you to know this thing by heart. Okay? It's really important. So this thing is actually equal to 4 pi R squared. How I remember it? What is the size of a circle? The area of a circle? It's pi R squared. Just 4 of them. Okay? Good. So this is dying out, right? This is dying out, right? And what I actually end up with is this. Q divided by epsilon 0. And this is actually Gauss's law. Gauss's law said that the flux is equal to, the flux is actually equal to what? This is the definition of the flux. E dot dA. But this is equal to, this is the definition, it's the same thing, right? Equal to Q divided by epsilon 0. And Q is actually the charge inside A. Okay? Got it? Let's draw it in a different way. I think this is going to be nice to have. This, and this is Gauss's law. Okay? Understood? Good. So, things that I want to tell you about it. Note that Q can be actually many charges. Okay? I don't care about a specific charge. It's all the charges that inside the area. So I added here a sigma. You see it? Okay? So here we have a sigma. So let's solve another equation. And something I want you to know is that this thing is called, as we mentioned before, Gauss's law. And this equation is so important, okay? If I need to choose only 5 equations for the exams, this is one of them, okay? This is a trick to find the electric field, which is more convenient than the one we learned before. Then KQ divided by R squared, this is going to be a horrible situation in many cases. This is going to give us a shortcut, okay? So this is a really fundamental, so fundamental in physics that this equation actually called Maxwell second equation. Maxwell was taking all the data that we gather about electromagnetism and compressed them into 4 equations, okay? This is one of them, okay? So it's really important. We're going to see this name coming as long as we proceed. But for now on, this is Gauss's law, and another name is Maxwell's second equation. Good. Like we have Newton's first law, right? Newton's second law, third law. So this is the parallel idea. Maxwell second equation, Maxwell first equation. Okay? Perfect. So I want you to note some important ideas. Okay? The flux sometimes can be 0, or can be positive, or can be negative. Okay? It's only telling me, let's do this. Let's do here. The flux can be sometimes 0. It doesn't mean that the electrical field in space is 0. This is not true. It means only the flux is 0, and if the flux is 0, Q inside A is 0. This is true. Okay? If the flux is positive, it doesn't mean that the electric field is positive or stuff like that. Okay? It just says that the electric field that leaving the shape, yeah, let's do E leaving, E out, is stronger than E in. That it's going inside, right? Inside, toward the sphere, okay? Inside, outside, okay? And the same idea here, okay? But it do tell me that the charge, the total charge, the total amount of charge is actually positive, or the total charge here is negative in this situation, okay? Okay, I want you to know that because I see a lot of students jumping to this conclusion, which is not always holding, okay? You're going to see it in the examples. Good. So, I'm going to this board, okay? I want to give you a small summary of what we talked. So what I want you to know, it's Gauss's law. Gauss's law is fundamental law of nature. Okay? Nobody prove it wrong. It's always hold. The interesting question you need to ask yourself, does it helping me right now? Do I can use it? So when you're going to use it, when it's relevant questions, do you have a relevant question to solve with that? I'm going to give you the hint that if you're going to see a symmetry in the problem, okay, Gauss's law going to do stuff really easy. Which means if you're going to see, for example, this symmetry of a sphere, it's going to be helpful. If you're going to see symmetry of infinite plane, which we're going to talk about it, it's going to be helpful. And infinite cylinder, usually when you hear the word infinite, Gauss's play along, okay? The only exception is spherical, okay? So here, it's going to be helpful. Okay? Good. So I'm going to give you another sphere example. Okay, so right now we have a sphere. This is a sphere. Hop, hop, hop. And now the charge is actually distributed on the surface. This is the charge. Okay? It's on the surface of this. Let's think it's a bubble that's charged with electricity. Okay? So this thing is charge. And the total amount of charge is, let's call it Q. Okay, some positive Q. Good. And I want to ask you, what is the electric field? What is the electric field in the world? Okay, in all space. Got it? Understand what you're looking for? So I want you to know that you can solve it with Coulomb's law. You can solve it by E equal K Q divided by R squared. This is like immediate, you can use that. You can say every piece of charge actually making this thing, right? With dq, and you need to sum them all. It's going to be complicated, and we can solve it really easy with Gauss's law. I look at this thing, and I see a spherical, infinite plane, infinite cylinder, and infinite, also a cube. Also some cube. Also can. Let's do, okay, sorry. Here I want to say that if this thing have a length, it's okay. But it's infinite in that directions. Okay? Okay, so this kind of like taking the cube idea. We're going to see it in another example. Okay? So if I want to find the electric field, I need to choose area. Okay? Let's solve it with Gauss's law. So what the area I'm going to choose? If I want to take advantage of this shape, I'm going to use the same shape. Okay? That's a small hint what area to choose. So I'm going to choose a spherical, right? A spherical, okay? Let's write it down. So phi E, I want to find the flux, is equal to the integral E dot dA. Yes? And according to Gauss's law, I know that this is equal to what? To the total charge Q in A divided by epsilon naught. That's what I know. Okay? Good. So right now, I need to solve both of them. So I want to calculate the electric field in two different places. One is inside the sphere, and one is outside the sphere, right? So we're actually gonna separate it. Okay, so here I must put this thing, right? Because I'm gonna choose a closed area. And this is, I can choose this area, right? This is an area inside the integral. Inside the area. And this is, okay, let me correct. This is an area that I took outside of my head that I want to use it to solve the problem. Okay? The black one is a real bubble that exists in the real world. Okay? It's clear? So I'm gonna do two different Gausses. One of them gonna deal with R that is smaller than the radius of the bubble. This is a bubble, R. And one of them is gonna deal with what's going on outside of the bubble, R. Okay? Clear? Good. So what I want you to notice that the electric field must be a function of R. Okay? Why so? If I look at this, for example, this point in space, okay, and this point in space, and this point in space, let's think that they have eyes, okay, these points, camera. If we're going to take a picture of a sphere in space, I would not have anything, any knowledge where I am beside what is the size of the sphere. It's small, it's huge, it means I close, it's small, it means I far away. That's the only thing. If I'm going to put a camera here and give you the picture to see, you would not know, right? You're only going to know my distance. So in space, the electric field must be a function of R and R only. Not theta, not phi, okay? This is clear? Good. So this is because of what? Of the symmetry. The spherical symmetry. I'm taking advantage of the symmetry. Good. And we said that we have two options, right? For the integral. And also for the electric field. One is going to be outside, the one will be inside, okay? Outside, sorry, let's do it the other way. This is inside, inside and outside. I have two options to solve it, okay? So in the general case, no matter what I choose, the electric field and dA is also a function of R, right? You're going to build this thing or this thing, right? That's all, right? But when I choose only one single R, they're using the same R. You understand? You understand the concept? So I can actually take this thing outside. R is a constant, also for dA and also for ER, okay? So E is outside the integral. This is ER, and it's getting multiplied by dA. Clear? dA is equal to what? I ask you to remember it by heart. 4 pi R squared. This is the general R. Okay? General R. Good. I'm going to this board. Here in the famous Maxwell equation, don't forget this. Okay? It's only hold for a closed area. If the area is not closed, it's not working. Okay? Good. So we have here on the left hand side ER multiplied by 4 pi r squared, and this is equal to what? To all the charge inside the area that I just invented from my head and tried to use it to solve the problem. Okay? Good. So now I have two situations, right? For the charge actually. If I'm inside the sphere, we talked that the charge is only distributed on the bubble, right? I'm inside the bubble. I see the bubble all around me. Hey, there is a positive charge. There's a positive charge there, but the sphere is smaller than the bubble, right? Let's talk about this situation. R is smaller from R. So Q inside my area is what? It's 0, okay? It's immediately 0, okay? What's happened if I'm outside of the sphere? I capture all the charge, right? I see the sphere. It's really small, it's here, and I'm around this sphere, right? Around the bubble. I see the bubble, I collected all the charge, I capture all the charge inside. So right now Q in A equal to all the charge that I have. Okay? Good. And now I can find the electric field. So in this situation, the electric field is equal to this thing divided by that. Q in A, this is just a Q. Q divided by 4 pi r squared, right? And this thing is actually saying that the electric field is 4 pi r squared equal to 0 divided by epsilon naught, right? I forgot here epsilon naught. Epsilon naught, right? This is 0. This is 0. Look, this is a constant. It's a specific R, okay? I agree this is a R that actually is smaller than the capital R, but it's smaller than that, but it's a constant. So this can be divided, and the electric field inside is equal to 0. This is in, this is out. Okay? So you can, if you want, use the Coulomb equation and calculate it and see that the all electric field inside the sphere is 0. You're going to sum all the contribution and then say, oh, fuck. It is 0, and it's going to be the correct answer. Okay? And outside of the sphere, we're getting this result, which is that, you know, this is K, right? K, Q, R squared. This is actually like a point charge. If I'm really far away from the sphere, it makes sense that this is like a point charge to me. But also if I am really close by, it's actually also look like a small charge in the middle. Okay? It's the same idea. Let's put it into a graph, so it's going to be easier for you to see. Okay. So if I'm going to put it in a graph, the charge, the electric field in space, this is, let's draw here space, this is the bubble, right? This is the distance, capital R, right, R, and this is a general R. So the electric field inside the sphere is 0. But the electric field as you go outside is actually have the value K, Q divided by R squared. And this is actually this decay going like R squared, KQ. Okay? Understood? Okay, so this is the electric field from a uniform sphere. Okay? Good. So this idea now was kind of introduction to the concept of Gauss's law, because I know that Gauss's is the most confusing concept in the class. Okay? So that's the reason I added this introduction, and I think that right now the problems would be easier to solve. Right now, with the time left, I'm going to start to solve some exercise regarding Gauss, a more like, hard question, kind of like exam. And next time we're going to meet, which is going to be this Wednesday, okay? This Wednesday there is a class. I'm going to talk to you about it after the class ends. And we're going to continue this equation, okay? This equation. So as I told you before, right? I hope that not a lot of people call me. Because I was not answering. But the same idea happened in a submarine. So I want to do a question about the submarine. So I'm going to go to this board, and I'm going to draw for you a submarine. Okay? So in this question, we have a really nice submarine. Let's draw it. The black, I want the black one. Here it is. So we have the body of the submarine. We have windows to see what's going on in the water. We have this periscope. We have water, right? And I also going to give you an axis, right? So you can understand where are you in space. And let's give also a nice propeller so this can move on. Good. So right now I'm going to draw an axis which is going to be 3D. So be careful. This is my axis, okay? This is the x direction. This is the z direction. And this is the y direction. And the shell of the submarine is actually charged. In which manner? It charged as a function of x. It's looking like this. A really complicated charge distribution. Rho 0 multiplied by x squared divided by d squared. And now you need to ask, what is d? So I'm going to give you, this is the wall from side view. Okay, this is our axis, z. This is going to be y, and this is going to be x. Okay, if we have a fish, so the fish is approximating the submarine. Okay, this is the fish. So the fish look at the submarine. This is the wall. This is you inside the submarine. Okay, having fun. Okay, you inside the submarine, here is water. This is the fish. Okay? Understand how the coordinates look like? So this distance is d. Understood? And how does the charge distributed? As x squared. Which means at the end of the wall, we have a lot of charges. You see? A lot of charges, but in the middle here we have 0. And it's like gaining more and more charge toward the end. You see it? Perfect. Good. So the question I want to ask you is, using the symmetry, okay, the symmetry of the infinite, I'm going to write it down, okay? So using the symmetry of I'm going to explain it, don't worry, infinite wall of the submarine, yeah. What is the direction of E? Which means, what is the direction of E? Okay? So if I'm a fish, and I'm standing outside of the submarine, I want to know what is the electric field that I have. And this is a really important question because a lot of creatures from the sea actually know and sense electric and magnetic fields. I don't know if you know it, but sharks can actually understand and feel electric fields and magnetic fields. That's the way they actually understand where is there something to eat. They look for the electric field and magnetic field that our heart produce, okay? And I don't know if you know, there is a cool startup that actually made a bracelet throw the leg, and surface can go with that and not getting eaten by sharks. So this is a really cool thing. Okay, so let's do this idea, but before I want to explain to you what is this concept, infinite wall. Okay, in real life we don't have infinite things. Okay, it's a lie. We have it only in math. Okay, so remember that we talked, let's think about it as a ball. Okay, remember that we talked in physics 1 about momentum. So this toy was having a mass, and if I want to understand the collision between the fish and this gigantic building, okay, what is the mass of this thing? I don't know, a few grams. And what is the mass of the building? Insane. I don't know how to calculate it, but it's going to be redundant, because every time I'm going to see the fish standing in the equation next to this big mass, I'm going to say this is infinite and killing that. I don't care about that, right? Right now, if we're going to measure my weight, this would not change almost anything, right? So when you hear infinite wall, the idea is that for a fish that's really close to the wall, it's look at the wall of the submarine, and you see, I don't see the end of the submarine. I don't see it. Look to the y direction, I don't see the end. Minus y, I don't see the end. Minus z, I don't see the end of the submarine. It's huge compared to the fish. What it's actually saying is saying that the fish is really small and really close to the submarine. So for this concept, this is an infinite wall, and you see this word? Symmetry, okay? So this is telling us something. So let's understand what is the direction of the electric field. So I use a concept that you may be more familiar with, okay, from our previous tutorial, but I think it's going to be a good recap, okay? So let's draw it in other direction. This is the fish, right? Okay, bubbles. And this is the wall of the submarine, okay? This is the wall of the submarine. Got it? The fish is above the axis. This is Z, this is Y, and this is X. Okay? So let's examine one piece of charge. What is the electric field that this piece of charge actually producing on the fish? In which direction? Only the contribution from that one. It's going to be pointing outside, which means this is the direction of the electric field. Understood? And what is the direction of this thing? The same thing, right? This is going to make electric field of this. So what is the contribution?